So in this video, I'm going to talk about the surface area calculation um, by using BET theory. So BET theory, we learned that um, the slope equal to C minus one V um, mono into C, and the intercept equal to 1 divided by V mono into C. So now I'm going to just add these two equations, the slope and the intercept. I'm going to add slope plus intercept, slope and the intercept. Okay, then this is, you can write this, I can cancel plus 1 minus 1, then C divided by V mono into C. So C can be cancelled, therefore 1 divided by V mono. Therefore V mono, that is V mono, the volume of adsorbed gases to form the mono layer will be given by 1 divided by this the summation of slope, and it is so V mono can be calculated using slope and intercept. You plot in the y-axis. You perform experiment, and you find out the P and V total, um, P naught minus P, and you find out this, and then plot in the y-axis, and in the x-axis you plot uh, P divided by P naught. Then you will get a curve. You'll get a straight line, and you find out the slope and the intercept for the straight line. You find out the slope and the intercept, and you add slope and intercept, and you take inverse, and you can find out V mono, that is volume of gas that is required to form the mono layer, for to form the complete monolayer formation, so from this V mono, from this data, you can find out the surface area of the adsorbent. Let me explain how we will calculate V mono. Volume of gases, volume of adsorbate for the formation of monolayer. Then you would have seen this curve, a type 2 curve, where you see this point corresponds to completion of monolayer. This point is somewhere x. This point actually corresponds to the volume. This corresponds to the completion of monolayer. This is volume of adsorbed material and pressure. The this Vm is actually, this is the volume which actually corresponds to this point, or the volume of gas adsorbed to form the monolayer. Let me use this ideal gas equation in RT. From here, I can find out V. I can find out N is actually N equal to P naught Vm by RT, where N is actually the number of moles of gas adsorbed. The number of moles of gas adsorbed. The number of moles of gas adsorbed at this temperature. um, and you know what is Vm? You know, Vm is volume of gas corresponding to this point, or the volume of gas that is required to form monolayer. And let me let the beta is actually is a surface area occupied by a single gas molecule. It is a surface area occupied by a single gas molecule, by a single gas molecule. So from this data, I'm just going to find out. I'm going to write an equation which gives total surface area. So therefore, total surface area equal to um, you know, the number of moles, the number of moles of gas absorbed at the monolayer. Number of moles of gas absorbed at the monolayer is given by P naught Vm divided by RT. This is RT, if we say 0. This is to show that standard pressure temperature, STP. This is at standard temperature and pressure. So this value actually gives the number of moles that is required to form monolayer, number of moles of gas that required to form monolayer. If you multiply with Avogadro number, you will get number of molecules present. Then if you multiply this with the surface area, the surface area occupied by one molecule, this is beta is surface area occupied by one molecule. Then if you multiply with the total number of molecules, this gives you total number of molecules that occupies the monolayer. So if you multiply this, you will get the total surface area. So this is the idea. So for this you need Vm. Vm is called a volume of gas that is absorbed at the first layer, or volume of gas required to form monolayer. So this Vm is actually found using BET. You can plot. If you sum up slope and intercept and you take a inverse of it, you will get Vm. So from BET you can get Vm value. From this you can find out the total surface area of the adsorbent. That is the more usefulness of this BET theory. Now let me explain how to calculate beta. Beta is actually the surface area occupied by single molecule, or the cross section area. If you consider here, this is surface, you see this is one molecule. This one molecule actually occupies this much of space. What do you mean by, let me write in a large circle. You consider this is a molecule adsorbed on the surface. You see, this molecule actually this molecule actually occupies this much of surface. This much of surface this molecule occupies. Therefore, this is equal to the cross section area of this molecule. So therefore, beta is actually the cross section area of the molecule. So if you calculate the cross section area of the molecule, I mean the area that will occupy the adsorbent by one molecule, that is beta. So if you calculate this area, then you can find out how many number of particles are there on the surface. You can find out the total surface. So this is the idea. So then how will you calculate beta? Let me explain it. The idea here is simple. Let me assume rho is the density of the adsorbent. Density of the adsorbent. density of the adsorbate. Rho is the density of the adsorbate, and m is actually the molar mass of the adsorbate. M is molar mass of the adsorbate. Molar mass of the adsorbate. Molar mass of the adsorbate. Now, rho density equal to mass by volume. Mass by volume. Here V is molar mass, molar volume. V is molar volume, right? Molar volume. Since rho is the density and m is molar mass, then V is actually the volume of that molecule. Mole, 1 mole of substance, for example. V is actually it simply you can say it is molar volume, right? Then molar volume. Let me assume this small v. This is small v to differentiate. This is capital V. To differentiate this with small v, I am writing this small v like this. You consider this is small v, and this is volume occupied. This is volume occupied by a single molecule. Occupied by a single molecule. This is volume occupied by single molecule. If volume occupied by single molecule is multiplied with Avogadro number, then you will get molar volume, right? Volume occupied by single molecule occupied by one molecule, when you multiply with Avogadro number, then you will get molar volume occupied by 1 mole of gas. That 1 mole of volume occupied by 1 mole of gas is called molar volume, and this is the idea. Then I'm just going to substitute this is molar volume. I am going to use this rho equal to m divided by capital V. So this capital V equal to small v. Small v is volume occupied by a single molecule into Na. This is equal to rho. Rho is density. From here I can find out small v, volume occupied by single molecule, equal to m divided by Na into rho. This is actually volume occupied by the single molecule, by the single molecule, right? Then let me assume the molecule to be spherical. Your molecule is a spherical molecule. Just assume it. Then the volume V is given by 4 by 3 pi r cube. From here I can write the expression for r. R is radius. It is 3 into small v 4 pi power 1 by 3. So I'm going to substitute for the small v. This is the expression for the volume occupied by the single molecule. So from here I can find out the radius. Radius is given by 3 into v. Small v is actually m divided by n into Na into rho. So therefore 3m 4 pi Na into rho power 1 by 3. So this is actually the radius of the molecule, the radius of the adsorbate. And now the cross section area. The cross section area is given by that is denoted by beta. It's already, I said, beta is cross section area of the molecule, is given by pi r square. So all r is already known. Therefore beta equal to pi into r square. R is already known, right? So this is 3m by 4 pi Na and rho into square. I have to square it, so 2 divided by 3. This is This is beta. Beta is actually, you know, the volume occupied by the single molecule is expressed by this equations, or it is also equal to the cross section area of the molecule of the adsorbate. So this is how beta is calculated. So if you know the beta value, see here, if you know the beta value, if you know Vm, and if you know all other temperature, pressure, and if you use all the terms, you can find out total surface area of the adsorbent. So this is the idea. This is how BET theory is used to find out total surface area of the adsorbent, total surface area of the adsorbent. So this, this data is very useful in catalysis and other part, nanomaterials especially. This part, this part is very important. BET isotherm is actually used to find out the surface area. This is very helpful in the catalysis, in the catalysis field. And now let me explain. Let me just look at this problem. I would like to solve this problem. Look at this problem. At 0 degrees Celsius, 1 atmospheric pressure, volume of nitrogen gas required to cover a sample of silica gel. So nitrogen gas absorbs on silica gel at 0 degree and 1 atmospheric pressure. So this is STP, standard temperature and pressure. Assuming Lang monolayer formation, monolayer adsorption is found to be 130 centimeter cube, per gram, 130 centimeter cube per gram of the gel. Calculate the surface area per gram of silica gel. Given that they are asking us to calculate surface area. So the data given is, they have given the monolayer, the volume of gas that is required to completely absorb only on the monolayer. So they have given the volume to form the monolayer on silica gel. And so they are asking us to calculate the surface area, and one more data they have given us, the area occupied by nitrogen molecule, by one nitrogen molecule, air nitrogen molecule. So area occupied by one nitrogen molecule is given, and then V mono is given. So this is what they have given. V mono is given, and beta is given. What is beta? Beta is actually the molecule occupied, the area occupied by one molecule, that is beta. Beta is given. So beta and V mono is given. And the temperature, pressure, you see here, temperature and pressure, temperature at 0 degree and STP, temperature and pressure is actually given, standard temperature and pressure. This experiment is carried out in standard temperature and pressure. Okay, this is the data. This is how you have to approach any problem. You first analyze all the given data, and then you proceed. And what I need is, they have given the volume. Volume of nitrogen gas required to completely fill the monolayer. If I find out how many molecules are present in this volume of nitrogen gas, then I can multiply that with the molecule occupied by nitrogen, one nitrogen molecule. Then if I multiply this data, then I will get the surface area. So very simple. So how do I do this problem? At standard, at STP, the volume of gas, at STP, the volume of 1 mole gas, 1 mole of any gas at STP, volume of 1 mole of any gas, 1 mole of any gas is given by 22.4 liter, 22.4 liter or decimeter cube. So this is known to us. And the data given is 130 centimeter cube of nitrogen. Cube of nitrogen, actually I have to calculate this much of volume of nitrogen contains how many molecules, this is what I have to calculate. And before that, this is given in centimeter cube, but I have to change this into decimeter cube or liter. How can I do this? I know 10 centimeter is actually 1 decimeter. If I cube this, I'll get centimeter 10 per cube, 1 decimeter cube. So 1 centimeter cube equal to 1 by 1000 decimeter cube. So therefore 130 centimeter cube equal to 130 in the 1 centimeter cube equal to 1 by 1000 decimeter cube. So this is equal to 0.130 decimeter cube. So I just change the unit from the centimeter cube to decimeter cube. Because I know at STP the volume of 1 mole gas is 22.4 liter. Decimeter cube and liter, they are same. So I have to change this centimeter cube into decimeter cube for my convenience. Then what I'm going to do, I said this is 1 mole of gas at STP, 22.4 decimeter cube. This is the volume of 1 mole of gas at standard temperature pressure. So this is the volume of 1 mole of gas. So 1 mole of gas contains 1 mole of nitrogen gas contains Avogadro number. 1 mole of gas is actually Avogadro number. Avogadro number is called 1 mole, right? Avogadro number is called 1 mole. So therefore this much of volume contains Avogadro number of this much of volume of nitrogen gas contains Avogadro number of molecules. Then my question is, then 0.130 decimeter cube of nitrogen volume, decimeter cube of nitrogen volume of nitrogen contains how many molecules? That's what I have to find out. So this can be found by just know the just know the logic. You just multiply this here. You just multiply on both the sides with 1.130. 22.4 decimeter cube into 0.130 into 6.023 into 10 power 23. So this gives 0.130. You keep decimeter cube and you take this 22.4 here in the in the denominator on the right side. 6.023 into 10 power 23 divided by 22.4. So this actually gives number of molecules present in 0.13 decimeter cube. Number of molecules present in 0.130 decimeter cube. This is, when you work out, you'll get this is actually number of molecules contained in V mono, that is the first layer of molecule, first layer of adsorption. Number of molecules that are present in the first layer will be equal to, if you work out this, you use a calculator, you'll know it is 3.4933 into 10 power 21 molecules per gram. 21 molecules per gram. Then area occupied by one molecule of nitrogen, occupied by one molecule of nitrogen, one molecule of nitrogen equal to nitrogen equal to 0.162 nanometer square. Nanometer square. So nanometer you convert into meter. So I'll get 0.162 0.12 into 1 nanometer equal to 10 power minus 9 meter. Therefore 10 power minus 9 10 power minus 9 square, 10 power minus 9 square is 10 power minus 18 meter square. So just converted nanometer square into meter square, into meter, nanometer scale into meter. I just converted. So now what I'm going to do, now 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 I calculated number of molecules present in this volume of nitrogen gas. The volume of nitrogen gas required to fill the first layer is 130 centimeter cube. So in this 130 centimeter cube of nitrogen gas, how many molecules are there? This much of molecules are there. So if you assume nitrogen on the silica gel is closely packed or closely adsorbed without leaving any surface, if you consider it is closely packed, if you assume the closely adsorbed, then if this much of molecule is adsorbed or occupies the whole surface area, the one molecule occupies this surface area. If this much of molecule occupies how much area will be calculated as follows. So one molecule occupies one molecule of nitrogen occupies 0.162 into 10 power minus 18 meter square area. Then 3.4933 into 10 power 21 molecules will occupy, you just multiply, will occupy, one molecule occupies this much, then this much of molecule occupies, you just multiply this two, you will get the total surface area 3.4933 into 10 power 21 into 0.162 into 10 power minus 18 meter square. This is per gram. If you work out, you will get 565.9 meter square per gram. So this is how you have to calculate the surface area of the adsorbent. So this is how you can solve the problem. So very interesting, based BET theory is actually successfully helps us to find out the surface area. So in this video, I just explained how to calculate the surface area of the adsorbent using BET. So just to recall what I have taught whole this video, just explained the surface area, how to calculate the surface area, and followed by how to calculate the cross section area of one molecule occupied, and from this data you can find out the surface area of the adsorbent. Okay.